Mhm. Hello, hello. I'm glad to see you could make it. Yeah, this is all kind of last minute. I wasn't sure if I could come in or not, but I decided not to because I don't want to cause any problems with my disease here. Well, it's just a cold, but still, coughing and sneezing is something I want to keep to myself. So anyway, what we're going to do today is the chapter 5 problem set, and then we'll get as far as we can into the sample midterm. And then when we come back on Thursday, we'll just finish up the sample midterm and start the next chapter. Well, actually, we started the next chapter already, so we'll just pick it up with that. I'm in my notes here, I've got it written down that we're going to have our midterm on Thursday, the 13th, a week from Thursday. So we should have plenty of time to wrap this up and then answer last minute questions. And so we're right on schedule. So why don't we begin? And as soon as we're done here, I will also, of course, as usual, be posting the answers on Moodle. Now, as far as the video is concerned, though, there will be a video for this class today, but unfortunately, the Moodle system doesn't seem to work well with videos. There doesn't seem to be enough storage. I don't know. I asked questions about this, and I was told that essentially don't put videos on Moodle because they may not fit or they may not work properly or whatever the problem is. So I'll be posting it instead of my YouTube account. Let me go get that for you. It should be easy to find it because I think all you need is my name, but if not, all you have to do is look at my correct YouTube name, I guess you call it, which is, no, there it is, that Dr. ACA. I guess that is my official YouTube name. And so if you type that in the search bar, it should come up with my account. And then what you'll find is there's a lot of videos from previous classes. So I'm going to create a separate playlist just for us so you can find it more easily. Yes, I do know how to do playlists. That's one thing I have learned how to do. But so that way, if you don't want to just aimlessly look around for it. So yeah, so there's a bunch of them already in there, but ours, from what I understand with this thing, you cannot create a playlist until you already have a video that's ready for it. So as soon as this recording is prepared, and it does take time to properly convert it into MP4 format. So it's not going to be ready for a while, but it'll be there. And so when it is, you'll go to my list of playlists and you'll see us. It'll be, of course, Math 1150, Monday and Thursday, spring of 23. By the way, you might notice there's a lot of others here, and you never know. You might be curious to look at some of these others. These are just old class recordings. You can feel free to look at them if you want. They're all open to the public. And so that's up to you. There's other stuff in here too. It's just a bunch of videos that I was watching. You don't need to look at that, but you can watch all the recordings that I made about the class and all the others too. So, all right, anyway, let's get to it. So this problem set is really not very long. There's not going to be, in this test, most of the focus will be on chapter 4, because I happen to think that exponential and logarithmic functions are more important than trig as far as applications are concerned, unless you're going into engineering or something like that. But at the same time, though, you will need this background for Calc 1 rather. So we don't want to neglect it altogether, but you'll notice on the sample midterm, the majority of the questions revolve around chapter 4 rather than 5. Okay. Now let's start with these. Now you're going to convert these angles to degrees. So just remember, the most important, I guess, way to remember how this works is to just recall the identity. Pi radians is the same thing as 180 degrees. So therefore, 3/4 pi radians must equal 3/4 of 180 degrees. Okay, and that's equal to 135 degrees. So that's all you have to do. Starting with this as your initial definition. Just adjust by the same fraction. That to me is the easiest way to do this. And then similarly, pi over 9 means 180 over 9, which means this must be 20 degrees. Now for this one, we know that negative means you're moving clockwise around the circle. So here's what I think is our best bet. Negative 5 pi over 4 would be negative 5/4 of 180, which is negative 225. But if you recall, with coterminal angles, that is actually correct. Remember, this means you're going clockwise through 2 full quadrants and into this second quadrant actually by another 45 degrees. So that means negative 225. But if we come in this direction, that means you're going 90 and 45 into the second quadrant. And so this is equivalent to positive 135. So your answer can either be negative 225, or you can rewrite it as positive 135. And you might recall that these two angles are said to be coterminal because they both have the same terminal angle. In other words, they both end up at the same point. It's like you have driven your car in 2 different ways, but you end up at the same place. It's like, imagine you have 2 different paths to get to school. Well, either way, you're still going to school. So you're going to the same point. And so both of these angles actually mean the same thing. It's just that one of them means you're going clockwise and the other means you're going counterclockwise. When both of these answers are correct. Okay, just want to point that out. Anyway, then pi over 3. So here's what we'll do. Actually, let me fix this. So if you're going to divide pi by 3, that means you also have to divide 180 by 3. And you'll end up with 60 degrees. Okay, so pi over 3 radians is the same thing as 60 degrees. It means the same thing. And again, the whole thing comes down to this identity right here. You've got pi radians, 180 are the same thing. All right. I'm sorry. So anyway, if anyone jumped in late, it's fine. Just be aware that this is being recorded. You can watch the recording, or you can just simply look at the solutions when I post them on Moodle, okay, later on. Now we're going to work this backwards. All right, so what would you do here? So you've got degrees, and we want to turn them into radians. So think about this. 90 degrees equals 180 over 2, which implies that it must be pi over 2 radians. Okay, so again, it all comes down to this idea that there's 180 degrees, or 180 degrees and pi radians represent the same thing. Actually, I don't know if you can actually ask your calculator to help you with this. Let me just check something out. You know that there is a pi mode in here, sorry, pi mode. There's a radians mode and then there's a degrees mode. I'm gonna try something real fast. Actually, no, I guess no. Now that I think about it, no, it's not gonna help here. It's different if we're trying to find a sine or a cosine or something. To directly convert from one to the other, I don't believe it has that capability. But again, all we have to do is remember how to do this algebraically. So now 180 by definition is just equal to pi radians. So you don't have to worry about that one. Now this negative 90. So negative 90 would be negative 180 over 2. That's negative pi over 2 radians. Now here's the thing though. You can convert this, or actually, you know what I'm thinking? It might be easier rather than going this way. Let's try it. Let me erase this and try this in a different way. I think it'll be a little quicker. 90 degrees negative means you're going this way. Okay, positive, the positive equivalent of this would mean you're going counterclockwise through 3 full quadrants. So 270 and negative 90 are the same thing. Okay. They're coterminal. So I think our best bet here is to not try to convert negative 90 into radians, but 270. Now, how is 270 related to 180? 270 degrees is the same thing as 3/2 of 180. Which means it must be the 3 pi over 2 radians. Okay. Now it didn't have to be done this way, but I think, yeah, that's your best bet. And then finally D, oh, geez, what do you know? 270. We just proved that 270 is 3 over 2 pi. So that happened because these last two, 270 and negative 90, are coterminal. They are the same angle. Okay. All right, now these trig functions. Now, oh, by the way, I did print up a copy of that slide, so I can Xerox it and hand those out when I get back to school. That slide in chapter 5 with the big circle. It has all the trig functions, which you don't really need it. I mean, it's nice to have it, but it's not absolutely necessary because your calculator is capable of doing any of these angles itself. Let's see if I can find that graph. You know the one I'm talking about. This one. Okay. So you can, if you want to, use this graph, but I think you should also get in the habit of using your calculators to do these. So, for example, or maybe use that graph as your double check. So here's what we're going to have to do. This can be found on the chart, the unit circle chart, I should say, or on the calculator. Now, if you use the calculator, it must be in radians mode. Okay, this is accomplished by hitting the button it's literally in the bottom left-hand corner. There is no other button further down there. All right, that's the last one in the bottom. All the way to the left, you notice how it says rad? The word, and you'll know you're in the right mode. Because the word rad appears directly above the parentheses. So let's try that. Hit the rad, and it is up there, just as a reminder. Now, then you can, so what you're going to need is the pi key, which is, it's slightly over from the 0. So here's what you do. Type pi divided by 6. Hold on 1 second. I need to check out the symbols box. Oh, it's here. If it would open for me. There it is. Oops, that's not what I wanted. There it is. Oh, no, that's not it. Okay, I don't use their equation editor because I can't stand it. Okay, I've accidentally got myself into a mode that I don't want. There it is. Jeez. Okay. Pi divided by 6 equals, and then whatever that result is, hit the sign button. All right. Actually, let me draw this out. Okay. I don't think you need parentheses for this. Just type pi divided by 6 equals, and then if you hit the sign button, it'll come back with your 0.5. All right, so again, pi divided by 6 equals, and then take the sign. Now, this is where the chart comes in handy, because you're going to look now and say, wait a minute. Where's pi over 6? Here it is. And you can see now, oh, you know what? Don't forget, when you look at these ordered pairs, this is the cosine, and this is the sine. So that's how you know you did it correctly. The sine of pi over 6 is 1/2. Either way, whether you use the calculator or this chart, you're still going to wind up with the same result. Okay, I'm going to move this out of here to save some space. All right, and so they'll all be done in exactly the same way. So for B, pi over 3. Just type pi divided by 3 equals sine. All right, so let's try that one. Pi over 3 equals sine 0.866. Oh, now, obviously this is some kind of a radical. All right, you can leave it like this, or you could try to figure out which one it is. There's only a handful of possibilities. It's probably radical 3 over 2. But if you're not positive, try it on the calculator or just come over into this chart. And here it is. It is, in fact, radical 3/2. All right, that's what you have to do. Now, the next two are cosines, obviously. We'll start with pi/6 equals cosine. Pi/6 equals cosine. Oh, how interesting. Well, clearly it must be radical 3/2. If you look at our chart, cosine pi/6 is this one. Yeah, radical 3/2. In fact, if you notice these two, not that you have to memorize this or anything, but 60 and 90, the two are reversed. A half in radical 3/2, here it's the other way around. Now, if you kept doing all trig functions all the time, eventually you would start to have this memorized, but we're not going to use it that often. Okay. And one more. Cosine pi/3. Now remember, pi/3 is 60 degrees. So that means it's going to be a half. All right, well, let's just prove it. Pi divided by 3 cosine, it is a half. Okay, 60 degrees or pi/3 up here. And again, don't forget, the first term is the cosine, the second one is the sine. And that's it. We're done. Now, here's the thing. Don't forget, when you're done here, to return to degrees mode. And you'll do that by hit the DEG button. The rad message above parentheses will disappear. So it's kind of strange that what they decided to do is rather than show degrees or radian on the top, it only shows radians if you're in that mode. If you're in the degrees mode, it doesn't show anything. I guess they figure most of the time you'll be in degrees mode and you don't want to be distracted by that. I don't know, it seems like an odd choice to me. Because now we're going to do the opposite. Now look how easy this is going to be. Oh, I'm sorry, this is not what I thought it was. Reference angles. All right. So remember how this works. There's again a nice little chart here. Oh God, where is it? There it is. You know what? I'm wondering if maybe I should copy this one too. In the first quadrant, the reference angle is the angle. In this second quadrant, the reference. It's not quite enough space here. And this is for degrees, by the way. 180 minus angle. And then down here, we reverse it. And in the last or fourth quadrant, it's 360 minus angle. So 90, the reference angle would be 90. Because we're still in the first quadrant. The next one, 240. Let me split the screen up for a second here. Oh, it doesn't want to work. There we go. What I wanted to do is have the graph. There it is. There it's good. So for 240, we're in the third quadrant. So therefore, the reference angle is 240 minus 180, which is 60. Now, minus 170, in my opinion, the only thing you can do with this one is to make it positive. Otherwise, you'll never get it. Okay. Now, I did show you that rule of thumb. We don't even need to draw the picture here because when it comes to coterminal angles, the reason why we know these are equal to each other is because their absolute values add up to 360. If you're not sure, draw the graph. Okay, but just algebraically, the fact that they add up in absolute terms to 360 means they must be reference angles. And now 190 is in the third quadrant. And therefore, we have 190 minus 180. And that's 10. Okay, great. And then the same thing for number D, it is also a negative. And so these are equal to each other because, I guess I shouldn't say they're equal. They're coterminal with each other. They represent the same thing. Okay, and now this is again in the third quadrant. Which implies that the reference angle is that angle minus 180. 45 degrees. Okay. Now for these, we're going to use the same setup, except they're pi, which means they're radians. So I'm going to steal this graph. Oh, I don't need this. Maybe I'll center it a little bit better. What's different now, though, is that we're going to replace some of these numbers with radians. You know what? I'm just going to draw this. This is such a mess. I'm just going to draw it all over again. All right, let's do it this way. So the first quadrant, it would just be the angle. The second quadrant, it's pi minus angle. Instead of 180, it's pi. The third quadrant, it's angle minus pi. And again, all I'm doing is trading or changing the angles. 180 becomes pi, but in this last quadrant, we have to, it's 360 minus the angle. We'll write that as 2 pi minus the angle. Okay. Now we can just do these. I'll just copy these down here so we can see them better. All right, so we'll split the screen. Okay, good. Now we can read these very easily. So 2 pi is 180 degrees. It's in the second quadrant. So, oh wait, I'm sorry. 2 pi is 360. So the reference angle would be 2 pi minus 2 pi. This is in the fourth quadrant. And it would just be 0. Okay. 2/3 pi is equivalent to 120 degrees, which puts it in the second quadrant. So that's going to be pi minus the angle, 2/3 pi, which leaves us with 1/3 pi. Okay. 5/6 pi, that's 150 degrees. And that's going to be in the second quadrant, so the same setup. Except that the fraction is 5/6. What you're left with is 1/6. Now, what about this one? 7/3 pi, where does that go? All right, well, just keep in mind, that means this is more than 2 full circles. This is more than all the way around the circle. Okay, so this is equivalent to 7 times 180 over 3, which is 420 degrees. This is equivalent to, this means going around the entire circle plus another 60 degrees into the first quadrant. So what we're going to do is we can then rewrite this angle as 60 degrees or pi over 3 radians. Okay, pi over 3 radians, which puts it in the first quadrant. And that means, as you can see in the first quadrant, the where the reference angle equals the actual angle of pi over 3. Okay. So that's, yeah, that one is a little challenging, but it just means that when it goes around the circle multiple times, just find where it stops and then apply the table. Oh my God. All right. Now for these will be a little simpler. Now, the challenge behind these is that we don't actually have these buttons. Well, actually, no, I shouldn't say that. The tangent is on your calculator. The others are not. Now, by the way, this chart that we were looking at earlier, the big circle, only shows the sines and cosines. Okay, just be aware of that. If you want something else, you have to do the algebra yourself. So the tangent of pi over 6, you can just go right back to the radians mode and do this directly. Pi over 6 tan. And what do you get? All right, pi over 6 equals, oh, don't forget about the equal sign. All right, so in other words, what you're actually typing on the calculator is pi divided by 6 equals, and then when you hit the tan button, you're going to get a very strange result. .5, well, it's not that strange. 0.57735. Now, that is probably a function of radical, well, it could be either radical 2 or 3, I suppose. So I'll tell you what, we can leave it like that, but if you really want to know, let's start with radical 3. Let's divide it by 2. No, that's not it. Radical 3 divided by 3. There you go. It's fine. If you get 0.577, it's fine. All right, great. Now, these next few require us to remember all of the definitions. Okay, so remember, this one is 1 over the cosine. Okay. So if you go to the calculator, what you can do, there's a couple of things you can do. If you want to do it this way, you could figure out the cosine of pi over 6 first. Pi over 6 cosine, whatever number you get, it's 0.866. Now, remember, we don't have cosine pi, we have 1 over it. So the way you can get around that is to type this 1 over x button. And now you're going to get something strange, 1.1547. God, what is that? Well, like I said, you can leave it. But if you really have to know, let's say you're just dying to know which radical is that. Well, let's see, how could you get to that? I don't know if there is an easy way to do this. But I'll tell you what, if you look and try different possibilities, it turns out that this is actually 2 radical 3 over 3. Okay, but this is fine right here. The other option is to say, well, cosine pi over 6 is 0.866, which we previously determined to be radical 3 over 2. And then when you rationalize it, I'm sorry, what am I doing? No, we have to invert it. So this secant is 1 over this. 1 over radical 3 over 2, which is 2 over radical 3. And then, of course, then we rationalize it if we want to. And there it is. Okay. Now, C is what this tells us is that 1 over the sine of pi over 6. So what you might want to do is figure out the sine of pi over 6 first. And you'll get luckily for us, it's 0.5, and therefore you hit the 1 over x button, and you just wind up with 2. I like it when it turns out nicely. Beautiful. And of course, this one is very clearly the inverse of the tangent. So using the same approach, we can type tangent, or actually we'll type pi divided by 6. Equals tan point, there it is again, 577. We had that earlier, didn't we? This should be radical 3 over 3. Yeah, this is radical 3 over 3. Okay, well then therefore the cotangent must be oh, 1 times the inverse. And then we multiply this by radical 3 over 3. Oh, this is interesting. It's just radical 3. All right, so that one's done. All right, so that, okay, now we can get back to the sample midterm, where, like I said, it's mostly exponentials and logs. That's good. All right, so we'll fill these in first. Now, of course, as always, there's plenty of fill-ins to go around, but they're very straightforward fill-ins. The standard form for the exponential function is f of x is a b to the x, although we've done other things with it. We've used these, and we've used n's, and we've used t as the independent variable, but this is the basic form. Okay. The domain for an exponential function, easy. It's the entire real number line. Okay. In other words, there's no value of x that can cause this function to either give us division by 0 or lead us to the square root of a negative number. Okay. If you remember, no matter which ones we drew in Symbol Lab, it covered the entire horizontal axis. The range is a completely different matter. Okay, the range is going to be restricted to either the positive or the negative numbers, depending on the sign of A. So what we have to do is say, if A is positive, then the range will be the positive numbers, but not strictly positive, not including the zero, that is. If A is negative, then we have the opposite, negative infinity up to, but not including zero. The horizontal axis is always going to be an asymptote here. Now, we have a couple of applied questions here. I like that. Compound interest. This is interest on interest. And then we have simple interest, which is interest on principal. All right, so all the interest that you earn or you're paid for a loan will consist of both. Interest on the principal is the simple. The rest is the simple interest. The compound was what's left over, basically. The base of log x. Now, just remember, this is just shorthand, because it just looks nicer, I guess. So the base of log x is therefore e. Okay. But that's why, because ln is simply an abbreviation for that. Now, common logarithm is the name that we give to a log of base 10. Only because you see it fairly regularly in scientific applications. Base 10 is a common result, although it's not always obvious. It's in disciplines like finance and economics, we tend to see natural logs more often because of the way it's related to interest rates, among other things. Now, this one looks like we need to run to our calculator, but we don't. Here's why. The log of 1 will always be 0, regardless of the base. This is because any number raised to the x power, 0 power rather, equals 1. So it's a bit of a trick question. Okay. Maybe I shouldn't call it a trick question, but now you can do this on your calculator, but remember the calculator doesn't have base 3. We do have a conversion formula though. And I'll tell you what, let's go into the slides and remind ourselves what that looks like. Just in case it comes in handy. We did at one point show there's a conversion formula so that you can actually in principle calculate any log you want. Oh, by the way, don't forget, switch your calculators back to degrees mode if you're not already there before you forget. Okay. In fact, I was supposed to mention that in the document. Hold on. Oh, I've already put it away. All right, it's fine. So here there's a formula that we can use. I think it came before this. Here it is. Yes. Okay. So, for example, with our case, what you could do is if you really wanted to go to your calculator, alternatively, we can solve on the calculator as, and it would just be the natural log of 1 over the natural log of 3. All right, so as we can pick any base we want in this ratio, but this number goes on top, this goes on the bottom. Now, natural log of 1 is just 0. It doesn't even matter what log 3 is. So you're just going to end up with 0 over something. Let me just quickly get that out. Natural log of 3 is, it's about 1.0986, but it doesn't really matter because you can see that we're going to get a 0. That's why I said the base is irrelevant, because the numerator is natural log of 1, and that will be the case no matter which one we try. And so this has to be 0. Now 9, e to the log x. Just be aware that, again, this is log e of x. And so what's basically happening is that you have e raised to a log base e. These, in effect, cancel each other out, and you just end up with x. Okay, because e raised to an exponent and log base e are inverse operations of each other. And so no matter what x is, this will give you an x as your result. And if you want to prove it with some examples, you can try it. Go to your calculator and put in, let's say, log 10, and then e to that result, and you will, in fact, get it, just at 10 back. And guess what? 10 is the exact same thing. All right, because log, this is simply base e, basically are cancel each other out. Log base e to the x are inverses of each other, and you still have x. Some very helpful properties. It helps us simplify a lot of horribly complicated equations. All right. Oh, well, I think we've done these before. The sine of 60 on this calculator. Now, if you're using one of the higher end calculators, of course, it's going to be slightly different. But the TI-84 also has sines and cosines and tangents. But if you want to switch to the radians mode, you have to go to the main menu, which is found from the mode button. Actually, should have mentioned this earlier. Hold on a second. I'm going to add this back to this document, because I was just assuming that you're using the phone, but you might not be. So let's see where I can sneak that in there. Okay, right here. Note, we switch to the radians mode. On the TI-84, hit the mode button and choose radians. You'll see on the top, okay. Oops. See, this is the risk with adding new stuff to a document. All right, that should be safe now. All right, I just wanted to make that clear. If you're using that one, it's a very simple matter. And then, of course, you have to remember to switch it back. Uh-oh. Oh, boy. Looks like I made a mess here. This is one of the annoying things about this tablet, though. It's if you change anything, it can really goof up the spacing. Oh, my God. What did I do? Okay, that's safe. All right, we're good. I was concerned for a minute there that I made a complete mess of this document. I've had that happen. All right, it looks good. Very good. All right, perfect. All right, so yeah, so going back to this 60 sine is 0.866, which we've seen so many times before. That's going to be radical 3/2. Now the cotangent of 90. Oh, and you know what, on this calculator, the TI-84, I think you have to, the sequencing might be different. If you type, I think you have to hit sine followed by 60. Yeah. All right. So it's reversed. Of course it is. You know, you'd think that all the calculators could get together, the function, I mean, the manufacturers, and say, hey, let's do it all the same way. No, that would be too easy. All right. So the tangent. But I believe tangent 90 is undefined. So let's find out. Yeah, I was afraid of that. Now you can kind of see why with the chart, which, oh God, I think I put it away. That's all right, we'll get it back. The chart. Here it is. Now you can see why, because the tangent, remember, the tangent is the sine of the cosine. The only problem is the cosine of 90 from this chart is 0. That's why we have a problem. Therefore, yeah, that's why. Okay. And therefore, the cotangent is also undefined. In fact, when we looked at these graphs in the class off Symbolab, we saw there's going to be many angles, 90, 180, 270, every one of those, you're going to have a problem. Okay. Okay, here, the cosecant is the inverse of the sine. All right, so that's what I have to remember. Cosecant theta is 1 over sine theta. Now, cosine of pi over 2. All right, no problem, but we have to switch back to radians mode. And then you'll get pi over 2 cosine 0. Well, that's right, because that's the one we were just looking at. Pi over 2 is 90 degrees. We just saw in the chart that that is equal to 0. All right, very good. Okay, then. Now, pi over 4 radians equals how many degrees? And don't forget to switch back. Okay, so this is how we handled it earlier. Since pi equals 180, pi radians, I should say, is 180 degrees. That implies that pi over 4 radians must be 180 over 45 degrees. Okay, so that's that. Now, here's some stuff that we haven't done in a while. Finding an exponential function that connects 2 points. So if you remember, we're solving simultaneous equations or substituting based on the formula f of x equals ab to the x. So if we have the point 2 comma 8, this is our x, this is our f of x. That implies that 8 is 2b Oh, yeah, that's right. No, we got it. 8 equals, oh, no, I'm sorry. I made the wrong substitution. Hold on 1 second. My fault, sorry. 8 equals AB to the second power, good. Because all we know is f of x and x. We don't know A or B, not yet, okay? Now for 6 comma 64, and 64 equals AB to the 6th. There you go. Okay. So we have 2 unknowns, 2 equations. So that should be enough to solve what we're looking for. Now, it's not going to be easy. These are very messy expressions. So we'll start with this one. 8 equals AB squared, which implies that, let's say, we'll solve for A. Substitute that back here to give us 64 equals 8 over B squared. B to the 6th. So B to the 6th over B squared is B to the 4th. And that in turn implies that 64B to the 4th is 8. Which is the same thing as saying that B to the 4th is 8 over 64. Or B to the 4th is 1 out of 8. And that in turn means that, oh boy. Well, that's a particularly unpleasant result. Well, it's not nice and even. Let's put it that way. All right, so let's just double check for a second. Oh, I know what happened. I goofed right here. Yeah, I knew something wasn't right. All right, you see why? Because this is not over. It's right here. This is the problem. It's actually right here. B to the 4th. That's it. Because again, it's B to the 6th over B squared. Now we're getting somewhere, okay? Because look how easy this is. So 64, now we divide by the, yeah, that's a lot more like it. I mean, it's not that it's a simple result, but we've got A to the 1/4 is B. Now, we could actually figure that out. It's a very small number, but for the time being, let's just leave it like that. Now, that result can be used to come back to this first equation And we have A equals 8 over B squared, which means yeah. Well, actually, this is working out pretty well because 8 over 8 to the 1/2 is 8 to the first minus 1/2. Let me just clean this up a little. So you've got A is radical 8. B is 8 to the 1/4 power. So the final result then is that our function yeah, it's not pretty. And if you want to rewrite it a little, no, I don't know. They're both pretty complicated, but that's what we have. Oh my God, what a mess. Okay. Now, sometimes they turn out fairly nicely, but often they're very messy. The next one is, here it is, 1,5 and 2,12. This is probably the worst problem of the group. The rest of these, in my opinion, are much more straightforward. Yeah, look how much fun these are going to be. Good. But you can see that we're not going to be done today. We'll finish this on Thursday. And then we can get back to 11, which, that very exciting chapter. All right, let's just do this. We'll keep going until, we're done. So for this one, we know that 5 equals AB to the first power. And then for this one, 12 is AB squared. Oh boy, look at how nice and easy this one is. A is equal to B, 5 over B. And then we also know over here that 12 over A is B. And so therefore, oh, you know what we could do? Hold on a second. Oh, that's fine. All right, that's fine. Go ahead. I just realized something. There might be a way of streamlining this a little bit. Let's try this. You too. Yes, I'll see you Thursday. Yes. I was thinking we could try this. Let's solve for A here too. By doing that, we can set these directly equal to each other. I don't know if this is going to help. And then we can plug it into either of the A's. So let's try this approach. So that means that 5B squared equals 12B Divide both sides by b. B is very nice. Very well behaved. B is 12/5. Now for A, we can pick this one at random. Since we know that A is equal to 5 over B, that means that A must be 5 over 12/5. And then we've got to be careful. It's so easy to goof these things up. This is the same thing as 5 over, or 5 times rather, the inverse of the denominator, which is 5 over 12. So that means A is 25 over 12. Wow. So it's not like exactly integers, but this is the nicest one we've had in a long time. So we just end up with 25 over 12 times 12/5 to the x power. And that's our exponential function. Beautiful. All right. So now we can get on to some interest rates. So this one is asking us about the future value of the sum. So that's this formula right here. Okay. And what do we know if the principal that has been saved is 50,000? It's a 5-year account. And the rate is 8, but the interest is compounded monthly. Okay. Hold on. So therefore, when we plug in the numbers, we'll have 50,000. 1 plus 0.08 over 12 to the 12 times 5 power. So you might want to think about simplifying it. The only problem is this ratio is actually 2/3 of a percent. So if you're going to round it like this, you can round it to a certain degree because this ultimately will be rounded to dollars and cents anyway. But here's what you're going to have to do. Just to be on the safe side, I'd recommend you keep 8 digits of accuracy here. It might seem like too much. It might seem like overkill, but just, you can't be too careful. Let's put it that way. All right. So now on your calculator, this is not a very complicated expression, but you might be better off starting with the expression on the right. On the phone, it's this button. On the TI-84, it's this symbol, okay? So this first number, 1.00666667, raised to the 60th power is approximately 1.4898 46, let's say. And then you can multiply that by 50,000. Oh my God, what the hell did I do? I obviously hit the wrong button, that's for sure. I very much have set my calculator, my computer here. Times 50,000 equals. And that's 74,492.30. Now, what if you do not want to get, now, by the way, this may not even be accurate within a couple of dollars because we rounded it. So what do you want to, if you don't want to round, to avoid it altogether, here's what you're going to have to do. You've got 50, let's copy this. You can do it, but you're basically going to have to do some extra steps. One plus 0.08 divided by 12. See, I have to think about what I'm doing here. This is so, because so that, in other words, what I'm saying is that rounding is nice. It avoids a lot of problems, but it may not give you the best result. No, that's not going to work. All right, something's not right. I think I'm missing an equal sign in here. I'm going to. Let's try that. Nah, something's not right. All right, I'll tell you what. We'll get back to this some other time. You just have to be careful to, if you're going to be rounding, just make sure you keep plenty of digits. We'll work on this one next time. We don't want to waste time with this. Especially since it might be different on every calculator. And in fact, it is different in every calculator. So for the time being, we'll just leave it like this. Just be aware that the more digits you keep, the more likely you are to get the right answer. All right. And then for part B, if we now compounding continuously is easy. Okay, because what you're going to do is this. So we had 50,000, 8%, 5 years. And you'll see the result will be somewhat bigger. So what you could do is solve for e to the 0.40. So again, every calculator is slightly different. On this one, you'll hit 0.4 on the phone, that is, and then e to the x. And then you multiply by 50,000, 74, 591.23. But on the TI 84, you would have to put e to the x 0.40. Enter. And then multiply by the 50,000. And then enter. And you'll have the same thing, of course. All right, so let's see. Oh, it's almost all right. I'll tell you what. What's next? Oh, evaluations. All right, you know what? Let's do a few of these and then we can call it a day. These are so straightforward. You're basically replacing all the x's with that one. So you end up with 6. And then for this one, now it gets a little trickier. And you can leave it like that. Although it turns out that that's equal to negative 1,220,000 billion. Ooh, 1,220,703,125. These next two will be very much more straightforward. Oh my God, look how easy this one was. All right, so the cancel the terms in the the exponent cancel each other out. So we get either the 0 or 1. And then finally for this last one, we'll have 5e to the 0 minus 1, 5e to the minus 1. Again, you can just leave it like that. But if you put it in your calculator, you'll see this is approximately equal to 1.83940. Okay. So then, yeah, we got some exponential growth problems. We still got a ways to go, but you know, I think we have already done the more complicated ones. So remember, our target for the test is a week from Thursday. So we'll carry on with this on Thursday, this Thursday. The test would be the following Thursday, which is the 13th, I believe. Yeah, that sounds right. And then, so we'll have a few more classes before the test. So we'll finish these up. We'll get back to 11, and then we'll do the test. All right, so we'll save the rest of this from 4 on until Thursday. And then by then I should be normal again. So we'll do this in the classroom. And then, okay, very good. So I'll post this part on Moodle. And when we're completely done, I'll post the complete set of answers. And then you'll be ready to go. Okay. All right. So I guess thanks for coming. Oh, wait, we have a chat. Yes. Okay, I will. I can tell already I'm better, much better than yesterday. That's for sure. So I should be fine by Thursday. All right. All right. See you all next time, everyone. You too. Bye.